about BaseJump STL.
All right, thanks. So my name is Dan Petrisko. I'm a member of the Bespoke Silicon Group at the University of Washington, Seattle. I'm going to be talking about BaseJump STL, which is a project that we use to launch our other research projects in our group. This was presented at first at DAC 2018. So first I'm going to start talking about something completely different, which is a really cool open source project that we have. This is Celerity. It's a tiered accelerator fabric with 511 RISC-V cores. The cool thing is this was taped out in less than a year. We just taped out V2 actually, which took about 6 months after the first tape out. We got 1.4 gigahertz on this 512 many-core with a monster knock with 300 terabytes of aggregate bandwidth. In fact, this chip actually set the world record for RISC-V performance with an 812K core mark bench score. It actually beat the last world record performance, which was Celerity V1, which beat the performance of the previous by about 100x. And the cool thing is, like I say, this is 100% open source. You can go and download the code today and check out the front-end RTL. The really cool thing is we barely wrote Celerity. 80% of the code was implemented with BaseJump STL. So BaseJump is this open source DNA for ASICs that we've designed in our group, and we've been using as a research platform and as just a way to tape out chips very fast and very agilely. So you start off with your HDL design. This is what everyone's familiar with. This is your Verilog, your chisel, what have you. We use BaseJump STL as this foundational template for how to design chips. This includes all of our plumbing, all of our primitives that usually get redesigned in group to group. There's also the BaseJump socket, which is an open source pad ring that we use to connect to the outside world. Fully placed and routed, it is PD optimized. We've manufactured BaseJump sockets, which you can use the standard BGA packages into your BaseJump motherboard with your BaseJump Open FPGA firmware. There's a theme here. And you can use something like a simple Z board to control this from a host interface. So you can use your DRAM controllers and everything like that. BaseJump's been used in many universities across the country. Many of them collaborating with us on DARPA projects, but some of them are actually completely independent that just saw our project, thought it looked cool, and tried it out for themselves. So I don't think we have to convince anyone in this room that hardware metaprogramming is a good idea. This slide was originally intended for DAC, which you actually do have to convince people hardware metaprogramming is a good idea. So I'll just skip over that. But the real core is that the state-of-the-art hardware design is that people write their own. People roll their own everything. There's optimizations that people use in their group, and they think that this infrastructure is unique and special in a snowflake, and that's just not true. We need to have some sort of a standard template library that you can use to customize all of your code and use as a foundation to accelerate. So in order for hardware to scale like software, we need code reuse to be the common case, not the exceptional case. We need to build great libraries that are able to be used with very little hardware overhead. When you use hardware metaprogramming, you can get this to near zero overhead, which is the ultimate goal. So there's many options for hardware metaprogramming. The very simple option that's adopted by many companies is to simply use something like Perl or Python to spit out Verilog what you want. This is the simplest. This is usually the most customizable because you can literally do anything in the language. And then as you move farther along the abstraction chain, you get to things like MyHDL and Chisel, which provide all the nice abstractions of functional programming, object-oriented programming, and all the nice programming things that come along with that. But I'm here to convince you that SystemVerilog is a good language, which is a very tough task. But SystemVerilog is a great language for a library because it doesn't require any additional buy-in from the users. If you provide a SystemVerilog library, you can connect that to pretty much any CAD flow. You can connect that to most front-end flows. You can link this with Chisel libraries, what have you. Verilog is really the lingua franca for hardware design. This is what is currently used to do hardware design, barring something like VHDL, which is also at the same level. So if we're going to use SystemVerilog for a library, we need to be able to use the hardware metaprogramming constructs. So let's examine what hardware metaprogramming SystemVerilog provides and how we can make this into a great library. So SystemVerilog provides generate fors, generate ifs. These are your bread and butter for metaprogramming. Parameters allow you to do things like customize the widths of hardware, but also let you do a lot more crazy tricks that people don't usually think about. And structs and interfaces are great abstractions for bundling wires together. This is how you avoid the classic Verilog module with thousands of lines just for the port declarations. And then last, there's macros, which, just as in C, are horrifying. But they're used to kind of put in what SystemVerilog doesn't support natively. This is, for us, things like parameterized structs, automatic sizing of things, and some safety constraints that we put in for assertions. So let's look at a good example of a good standard template library, which is C++. Everyone uses C++ STL. Generally, when you're coding, you basically think, how can I use the native data structures to do my project, not how can I build data structures to do my project. And the reason that this works is because you trust that these are best of class data structures. These are best of class algorithmic implementations. You probably won't be able to do better unless you put substantial engineering effort into this. And another key aspect that's often overlooked is that there's tight language integration. This is C++ and C++. You don't have to learn a second language. You don't have to monitor two build flows, things like that. And it provides this code reuse using the same data structure code. So if SystemVerilog supports map programming, why doesn't it have a standard library like this? And we argue that it does now. BaseJump STL is a great standard library that everyone should use. Not really. It's just getting started. BaseJump STL is used in real ASICs. You can use it today. You can use it to build very complex chips, and what's there is rock solid. But we need community buy-in to actually get everything that people need and all the interfaces really rock solid. So what do we need to make BaseJump STL successful? Number one is that this is a hardware STL. There is differences in software STL. Just the interfaces alone are not enough. Since this is mapping to real hardware, you need to provide a portability interface that allows you to use this standard template library for both ASICs, FPGAs, whatever targets you have. And we use what we call in the BaseJump the hard methodology for this. Essentially, you have your portable Verilog STL, which provides a synthesizable behavioral model of your, say, memory in this case. And then you use your Foundry-specific override files to wrap that in exactly what you need to feed into your memory compiler, feed into your FPGA VRAM generator, things like this. And this provides a very clean interface because you use the same interface between the soft and the hard files. And this allows you to hot swap them so that you can have the same file, not change any of your RTL, but use different backends in your build flow. And this methodology does work. For example, UCSD did an emergency tape out in 3 days, porting their 250 nanometer design to 180 nanometers. This would normally be months-long project, but using the BaseJump methodology, you're able to just hot swap these and have very little front-end overhead. Another building block is, or another requirement is to have leaf building blocks. These are the things that interface with the real world, things like SRAM synchronizers. Being able to portably use these leaf building blocks is important for a hardware STL. These are things that you can't always roll your own. You need to work along with foundries or FPGAs. So it's important that the STL is able to deal with this. The whole point of this is to have efficient hardware primitives, though. Instead of rolling your own, you're probably not going to do better than a normal implementation of a D flip-flop. And things more advanced than that, the real goal is to make it so that without significant engineering effort, you're not going to do better. We talk about Pareto curves as you're probably just going to start a small amount of effort, and if you really want a ton of improvement, you're going to need to put in a ton of time and engineering effort into this. So BaseJump provides very good hardware primitives for a wide variety of use cases. There's several hundred modules today in BaseJump. Things like data flow, FIFO, stream mergers, asynchronous components, which are always tricky. And we provide test modules. These are test bench blocks that do things like asynchronous reset generators, random generators, text inputs. And all of these components are easily searchable. We try to reduce the number of modules wherever possible by combining them using metaprogramming so that it's easy for a user to just go in and examine the code for exactly what they need. But all these components need to work together. And when you're doing a large ASIC design, you don't want to end up drawing hundreds and hundreds of waveform diagrams to make sure that your timing all lines up. So we use something called latency-insensitive design, which people may be familiar with. This is your ready-valid interfaces. Every component in BaseJump STL is latency-insensitive so that you can plug and play with all of them without considering a lot of the implications of this, of wiring them together. And these interfaces have very low overhead, zero overhead in most cases, but they allow wire delay to be managed in a portable way. So your typical ready and valid interface looks like this. You have your producer and consumer. The producer says, I have valid data, and the consumer says, I am ready to consume that data. And both of them know that when both valid and ready are high, we're able to go ahead and do our action. And in this system, valid and ready can't depend on each other, because by the time the valid signal propagates to the other side, the ready signal has already had to have been sent out. This is nice because it avoids a round trip, and it also has guaranteed no combinational loops, but it's not a general case. There are simple hardware primitives that simply cannot support this. If you have something that needs to select between many ready and valids and needs to commit to taking one, it will need to examine all those valid signals, do some combinational logic on it, and then redo the valid. Conversely, there's the opposite case where you have to choose what valid signal to output. So we call these in BaseJump demanding interfaces to contrast them with the helpful interfaces that provide their ready and valid signals at the beginning of the clock cycle. So there are really three interfaces that provide universality for connecting latency-insensitive modules. There's ready then valid, where the producer demands R up front and then waits for V. Valid then ready, which is the opposite. This is also called valid yummy in BaseJump STL terminology. And valid and ready, which is used for long-distance connections or just between two helpful interfaces. So these universal interfaces do have one bad case, which is if you have two demanding interfaces, you need to use a FIFO to convert them, because a FIFO has helpful on both ends, so you can strap anything together that way. So when we're designing the library, which of these do we want to use? Well, the answer is to be as helpful as possible without introducing new logic. You want every module to be helpful, but in some cases, you cannot convert the module from demanding to helpful without introducing internal buffering or without introducing significant logic to deal with the arbitration of having multiple signals. So the general rule of thumb is if you have to add more logic, then you may be better off just making the module demanding and hoping that you're connecting to a helpful interface. Another option for this is to have parameterization, which allows you to make the module demanding or helpful depending on your use case. And that brings us to parameterization, which is another great technique for hardware programming. This allows you to do simple things like change your widths, but it also allows you at a higher level to reduce bug count, reduce module count by factoring out the common cases and reusing as much code as possible, even internal to the library. This is how we avoid a lot of bugs from re-implementation. BaseJump also needs to provide a way to move the data around these hardware primitives. So these are things like FIFOs, virtual channels, credit counters. BSG NOC has dozens of these components, which are used in hundreds of configurations across BSG to efficiently pipe data across chips. And you need to be able to trust the code. So we use bug-reducing coding style in BaseJump, so you can look at the code and you're able to see exactly what's going on based on best practices of using common suffixes for names, using standard parameter names, and just being able to look at code and see, despite whoever wrote it in BaseJump, which is at this order of probably dozens of users now, possibly hundreds of individual contributions. With this common coding style, you can know exactly what's going on. And it makes it easier to use as well, because then you don't have to look up if someone said width or size or length. You can always just consistently know that the parameters are what you think they are. And another key point of this is that non-synthesizable modules are clearly delineated. Non-synthesizable parts of modules are limited to assertions and display blocks, which means that your synthesis results are going to match your front-end results as much as possible. Similarly, along with trust, we need a testing suite, which says if you stay within your invariants, which are the parameters that we've tested, then you're supported. This is a supported use case. And we do this in BaseJump by having assertions that bound the parameters to tested use cases. If you run into something that is not tested, you can try it out yourself and implement some more logic and then make a pull request back into BaseJump STL. The point of this is that, performance is the main draw. You want best of class data structures, you want best of class hardware. But at the same time, it's really all about the money. You have to reduce development cost, and by not rewriting code, by trusting a library code, you can spend a lot more of your time on your value add proposition. And one thing that's unique to a hardware STL is that in software STLs, you generally trust that implementations are fairly efficient based on some algorithmic scaling, whether that's whether that's area or performance. For a hardware STL, there's a lot more concrete numbers. And this is power, performance, and area for specific technology nodes. So for BaseJump STL, we internally have synthesis results for most of the modules for common configurations. And there's work in progress to support a full PPA regression so that BaseJump users can be able to see the actual power, performance, and area of all the components, be able to make informed trade-offs as to the architectural implications of using one FIFO versus another. And then also for a community perspective, so that pull requests can be automatically run against this and see exactly how these perform comparably to other implementations in BaseJump. So SystemVerilog is still not great. There are some problems, so I will complain about this a little bit because I still have some time. So some things that we would like to see in SystemVerilog to improve it as a metaprogramming language is synthesis support for arrays of interfaces. Currently, we have to split up interfaces into arrays of unidirectional structs. This is actually done usually at the synthesis level, where at the front end level, you can test with your interfaces, which have these nice, ready valid properties, parameterizable widths. But then once you get into the synthesis level, it actually splits them automatically, and now your backend scripts have broken because names have changed. So we stick with hard-coded arrays of structs, which leads to parameterization it's kind of difficult to do in SystemVerilog. Another thing we'd like is tolerance for zero-width signals. And this is a simple example would be a mux. Once you get down to one element, you don't actually need the select signal. However, it's still necessary because you have to have at least one bit in your signal. And this means that you have a wasted wire, which is not that big of a deal, but it also leads to problems when you're doing packetization or things where you're actually measuring widths. So it would be very nice to have. This would also allow you to rename signals based on parameters. Default parameters being optional is something that is very important in a library, actually, because if you just use a module and forget to set a parameter, or even worse, name something slightly off of what you think the parameter name is, you'll get some default parameter that's not good for you, and it won't match your hardware intent. And SystemVerilog allows you to set a default parameter, but for example, a lot of times people use something like quote INV for invalid, but that actually synthesizes to 200 or 2 million width signal, something like that. So you usually end up crashing in a very weird way. True type polymorphism would be nice for this. This is good for containerization. If you have something like you have a FIFO that you want to pass a struct to, instead of passing a width, you can pass a struct, and then it can wrap this very nicely and spit it in and out. Bit width inference would be nice for debugging. This is something that usually flags a very quiet linter error, but can cause very severe problems. And then better generated statement debugging. This is actually a feature in Verilator, which we use very heavily. We usually use VCS for our simulation, but we use Verilator for its linting and preprocessor, which are best of class. And then we'd like to see a language construct to indicate a signal's unused. So for something like a portability interface, you might have a slightly different interface between the synthesized module and the non-synthesized module, just to, because that's how they physically actually lay out. But we don't want the tools to erroneously flag that we're doing something wrong, because then that leads to confusion on the user side and on the developer side. So yeah, BaseJump STL is ready to be used in ASICs. We welcome you to use and improve our STL prototype. Thank you.
we have any questions?
Hi, do you support any standard buses like Wishbone or AXI?
We have chips that support AXI. I want to say some of the support for AXI is committed to BaseJump. Wishbone, I don't think we have any chips that support. Usually our model for how we add things to BaseJump is what we've used in our chips. We test, battle harden, and then contribute it back. So we'd be incredibly open to receiving contribution like that.
And also, what open source tools accept this level of SystemVerilog?
I'm sorry, I don't understand the question.
What tools will take the sophisticated SystemVerilog into open source?
Oh, sure. So we use Verilator for our open source builds for this. The synthesis is a little more tricky. We actually use this interesting flow. There's this, if you go to Bespoke Silicon Group at github.org, you can see this SV to V converter, which allows you to convert the sophisticated SystemVerilog to regular Verilog. Unfortunately, using Synopsys Design Compiler is an intermediate, but this will let you feed it into an open source, Yosys or something like that. And that's what we use for open source synthesis.
Thank you.
Yes, do you package your library to the IP-exact packaging standard?
No, we have not done that yet.
You've heard of the IEEE? You know they do these standards you're supposed to follow. Have you ever thought about following them?
Yeah, no, we're open to integrating into more official ecosystems. The real goal would be for us to no longer maintain BaseJump STL and have it be a standard library that's community owned. It's still in very early stages of adoption, so we're trying to get more official, things like that.
Have you thought about adding FuseLog support?
Yeah, Jonathan has been trying to get me to do that for quite some time. It seems like an ideal use case for it, right? Because this is something that could be imported to everyone's libraries. And we're definitely open to doing that. We haven't used FuseSock in our own internal projects yet, so probably the pipeline for that is we'll use it for a sophisticated project for our own, see how it works, and then see best practices for how to integrate it.
Well, thank you.
Thank you.